In the span of just 5 months, 2 brand-new Boeing 737 MAX aircraft plummeted from the sky shortly after takeoff, killing 346 people. These weren't isolated incidents of mechanical failure, they represented a catastrophic breakdown, not just in engineering, but in a complex web of corporate culture, regulatory oversight, and intense market pressures. Today, we're dissecting the real reasons behind these tragedies, peeling back the layers to reveal a systemic failure that shook the aviation world to its core. This isn't just about a faulty sensor, it's about decisions made at every level. The story begins with intense competition. Boeing, a titan of aerospace, faced a formidable challenge from its European rival, Airbus, specifically their highly successful A320neo, a new single-aisle plane. To counter this, Boeing needed a quick, cost-effective response. Their answer was the 737 MAX, an evolution of their immensely popular 737 series, aiming to deliver better fuel efficiency and capacity. The imperative was clear: innovate fast, or lose critical market share. This strategic drive set the stage for a series of compromises. To achieve the promised fuel efficiency, Boeing fitted the 737 MAX with larger, more powerful CFM LEAP 1B engines. But there was a problem. The 737's low-slung design meant these larger engines couldn't be mounted in the traditional position without scraping the ground. Boeing's solution was to place them further forward and higher up on the wing. This seemingly minor adjustment had significant aerodynamic consequences. It subtly altered the plane's handling characteristics, particularly at high angles of attack, causing the aircraft's nose to pitch up more aggressively than previous 737 models. To counteract the new nose-pitching tendency and ensure the 737 MAX handled like its predecessors, Boeing introduced the Maneuvering Characteristics Augmentation System, or MCAS. This was a piece of software designed to automatically push the aircraft's nose down if it detected an imminent stall, bringing the plane back to a safer flight envelope. The intention was to make the MAX feel familiar to pilots trained on older 737s, avoiding costly simulator retraining. It was an automated fix meant to paper over a fundamental aerodynamic change. On October 29, 2018, Lion Air Flight 610, a brand new 737 MAX, crashed into the Java Sea just 13 minutes after takeoff, killing all 189 people on board. The flight data recorder revealed a chilling pattern: repeated, uncommanded nose-down inputs. The pilots were fighting the aircraft, struggling to regain control as an unseen force continuously pushed the nose towards the ground. At the time, the full implications weren't understood, but the harrowing flight profile would soon become tragically familiar. Less than 5 months later, on March 10, 2019, Ethiopian Airlines Flight 302, another 737 MAX, crashed 6 minutes after departing Addis Ababa, killing all 157 passengers and crew. The parallels were immediately striking and horrifying. Once again, the aircraft experienced repeated, uncommanded nose-down inputs. Investigators found that the pilots were battling an automated system, trying desperately to pull the nose up while the plane fought back. 2 brand new planes, 2 identical, catastrophic scenarios. The world demanded answers. Investigations into both crashes quickly converged on a common culprit: the MCAS software. In both instances, flight recorders confirmed that the system repeatedly activated, forcing the aircraft's nose down. Crucially, the pilots were found to be overwhelmed. They were battling a phantom co-pilot, unaware of MCAS's existence, let alone how to disable it. The system, designed to enhance safety, became an unyielding force against human intervention, leading to an inescapable descent. The deeper analysis revealed a critical design flaw: MCAS was activated by input from just a single angle of attack, or AOA, sensor. This sensor measures the angle between the wing and the oncoming air, crucial for detecting a stall. In both fatal flights, a single faulty AOA sensor sent erroneous data, incorrectly indicating an impending stall. This triggered MCAS, which then commanded the nose down, despite the pilot's attempts to correct it. The system lacked the redundancy necessary to prevent such a catastrophic outcome. Perhaps one of the most damning revelations was the almost complete lack of information provided to pilots about MCAS. Boeing, aiming to minimize training costs and avoid expensive simulator time for pilots transitioning from older 737s, deliberately omitted details about the system from flight manuals. Pilots flying this 737 MAX were simply unaware that MCAS existed, let alone how it functioned or how to counteract its activation. This knowledge gap left them unprepared and powerless against a system they didn't even know they were battling. The pressure to compete with Airbus's A320neo, which had already secured significant orders, led Boeing to rush the 737 MAX development. This wasn't just about innovation, it was a race for market dominance. Every decision, from engine placement to software implementation, was influenced by the need for speed and cost efficiency. This aggressive timeline compressed testing schedules and encouraged shortcuts, ultimately compromising safety. The ambition to deliver a new aircraft quickly overshadowed the meticulous diligence required for safety-critical systems. Adding another layer to the systemic failure was the FAA's certification process. Faced with resource constraints and political pressure to streamline regulations, the Federal Aviation Administration delegated significant portions of the 737 MAX certification to Boeing itself. This meant that Boeing employees, under the company's influence, conducted safety assessments on their own designs. This self-certification model, while not entirely new, created an inherent conflict of interest, where the very entity responsible for designing the plane was also largely responsible for deeming it safe. Compounding the issue, the FAA's auditors, tasked with overseeing Boeing's delegated work, were often understaffed and lacked the specialized expertise required for detailed oversight of complex new systems like MCAS. They relied heavily on Boeing's documentation and assessments, often unable to conduct independent, thorough evaluations. This created critical blind spots. The regulatory body meant to be the ultimate arbiter of safety found itself in a position where it couldn't provide adequate scrutiny, effectively rubber-stamping crucial decisions. The initial design of MCAS stipulated that it would activate only if inputs from two angle of attack sensors agreed, providing redundancy. However, Boeing, to save cost and time, later changed this to activate MCAS based on a single AOA sensor. This fundamental alteration, which drastically increased the risk of a single faulty sensor causing catastrophic failure, was neither flagged as critical by Boeing nor thoroughly reviewed by the FAA. It was a significant downgrade in safety, overlooked amidst the rush to market. Originally, MCAS was intended for use only at high angles of attack and slow speeds, a narrow operational window. However, Boeing expanded MCAS to activate at lower angles of attack and higher speeds, covering a much broader range of flight conditions. This expansion was not accompanied by proper review or thorough testing in all the new scenarios. The system was now operating in regimes for which it was not adequately validated, creating a dangerous unpredictability that would prove fatal in situations with faulty sensor data. The environment surrounding the 737 MAX certification was fraught with pressure. Boeing employees reported feeling immense pressure to certify the plane quickly, impacting their ability to raise concerns without repercussions. Simultaneously, the FAA faced pressure from Congress to reduce the regulatory burden on manufacturers, creating a climate where efficiency sometimes trumped meticulous oversight. This confluence of internal corporate pressure and external political influence created an environment ripe for critical oversights. Following the Ethiopian Airlines crash, the global aviation community reacted swiftly and decisively. Country after country, starting with China and then swiftly followed by major regulators worldwide, grounded all Boeing 737 MAX aircraft. This unprecedented global grounding, which lasted for 20 months, was a stark testament to the severity of the crisis and the widespread loss of trust in Boeing's product and the FAA's oversight. Thousands of flights were canceled, and airlines scrambled to adjust their schedules, highlighting the immense ripple effect of these failures. The consequences for Boeing were staggering. The grounding of its flagship narrow-body aircraft led to billions of dollars in losses, canceled orders, and protracted legal battles. Airlines demanded compensation for financial damages, and victims' families sought justice. Boeing's stock price plummeted,
and its once unblemished reputation as an engineering marvel was severely tarnished.
The financial toll alone underscored the immense cost of prioritizing speed and cost-cutting over safety and thoroughness in aviation development. Beyond the financial penalties, Boeing's reputation, built over a century of aviation excellence, suffered immense damage.
For many, the incident eroded public trust in the company's commitment to safety.
Rebuilding that trust would be a monumental task, requiring years of transparent operations, rigorous safety adherence, and demonstrable changes in corporate culture. The crashes served as a stark reminder that in aviation, a company's most valuable asset isn't its order book, but its unwavering dedication to the safety of its passengers.
In the wake of the grounding, Boeing embarked on a massive effort to rectify the MCAS software.
Extensive software updates were implemented, which now require inputs from both AOA sensors and ensure that MCAS can only activate once per flight, preventing repeated nose-down commands. Furthermore, the system now works within much stricter limits, giving pilots greater control.
These technical fixes were crucial for regaining certification and ensuring that the fundamental design flaw would not be repeated.
A critical outcome of the investigation was the overhaul of pilot training protocols. Pilots now receive extensive, mandatory training on MCAS, including detailed explanations of its function, potential failure modes, and precise procedures for disengaging it. This training includes hands-on simulator sessions that replicate the exact scenarios encountered in the Lion Air and Ethiopian Airlines crashes, ensuring that future pilots are fully aware and equipped to handle any unexpected MCAS activation. The days of pilots being in the dark about critical systems are over.
The FAA also underwent significant reforms.
The agency revised its certification procedures, significantly increasing direct oversight and reducing its reliance on manufacturers' self-certification. More FAA personnel are now directly involved in reviewing and approving critical safety systems, ensuring a higher level of independent scrutiny. This shift aims to restore public and international confidence in the FAA's role as a robust and independent safety regulator, ensuring that financial pressures do not compromise the rigorous standards required for aviation safety. The Boeing 737 MAX crashes stand as a somber lesson on the perils of unchecked ambition and the critical importance of robust safety protocols. They underscore that in aviation, every design choice, every regulatory decision, and every training omission has potentially life or death consequences.
The industry must constantly balance innovation and speed with an unwavering commitment to safety.
For passengers, for pilots, and for the integrity of flight itself, the ultimate lesson is clear: no competitive advantage is worth compromising human lives.
The skies must always remain safe.